background noise is more clear than when you speak. So I think you have microphone.
Not speak, switch off your microphones, and I think we can finally start. So, good morning, everybody. Let me just to briefly introduce why this webinar is carried out. Actually, we met with Technology Center Mongstad representative, Mrs. Joran Britsan, during the conference for coal regions in transition in Katowice this year. And during the lunch break talk, we discovered the enormous technology potential of TCM related to the topic of carbon capture, use and storage, which is extremely important for our industrial region. From this time, we simply look for ways how to cooperate. And thanks to TCM and all their partners, namely Carbon Limits, DN, VGL and Gasnova, we may discuss this topic today. At the last part of the webinar, we will discuss the eventual opportunities for further cooperation, if you agree. And maybe before starting the presentations, let me pass the word to my colleague, Mr. Daniel Minařík, the energy expert from the city of Ostrava and the Technical University of Ostrava, who will shortly summarize the regional frame of our Norwegian colleagues. Okay, can you start, please, Daniel?
Daniel is muted.
Daniel, please switch on your mic. Well, not to prolong it, I see Daniel is here, but we can keep this part of information for after the presentation. So not to prolong it, let me give the word Mrs. Leila Farmati from Technology Center of Mongstad, and I kindly ask her to start with the first part of the presentation. Thank you.
Good morning, everybody. I try to keep my part as short as possible to make up for the lost time. We have 5 presentations today and some of the best experts in the Norwegian CCS field. And the first presentation is by Carbon Limits by Mr. Peter Brown, who is the principal consultant at Carbon Limits. And the topic of the presentation is European Green Deal, how the goals and ambitions affect the need for CCS and hydrogen. With that, Peter, please start.
Thank you, Leila. I will now share. All right. Okay, can you see the presentation?
Yes, that is good.
Yeah, okay, great. So thank you. My name is Peter Brown. I work in Carbon Limits, which is a consultancy in Norway, where we work with industries and governments on different climate mitigation topics, where CCS is one of the important topics we're working on. So just to start, we'll look at emissions today in the EU 28. There are about 4.3 billion tons of greenhouse gas emissions in 2017. Land use and forestry capture some million tons, and reduce it to about 4.1 million tons in net emissions. But if we look at the share here, we see that electricity and heat, of course, is large. Transport is large. Energy use in buildings and other fuel combustion is also large. Agriculture represents a significant share. And then we have the different industrial sectors, which, as they're grouped here, chemicals, metals, minerals, refining, they all represent about 100 to 180 million tons a year. So the European Green Deal is a roadmap that lays out the intentions and ambitions of the EU Commission. It's a communication document that's followed up with legislative proposals, strategies, and action plans. The keystone in it is to reduce EU emissions to net zero, and strengthening from the 80 to 95% reduction goal of in 2050 to net zero emissions in 2050. So it's been followed up with the climate law, with a legally binding target for net zero emissions for the EU as a whole, and a number of legislative packages are going to be revised there. Also, in the shorter term, the Commission is working on a proposal to raise the target for 2030 to from 40 to 50 to 55%, and will present their assessment of this this fall sometime, which will also have a short-term effect on emission prices, and also a number of other initiatives are mentioned, but for CCS and for hydrogen usage, perhaps the most interesting ones are the carbon border adjustment mechanism, which is a mechanism to ensure that emission regulation and pricing doesn't lead to carbon leakage for industries, and has been proposed to suggested to be tested on certain industries. Also, the EU is planning a strategy on clean steel to reach net zero steel production, and the hydrogen strategy is announced that'll come sometime later in June. So, what does this mean? It means Europe as a carbon neutral continent. That means that those 4+ billion tons of emissions have to be reduced and gone by over the next 30 years. So it means that decarbonization of power and heat must be done massively, which is underway. Renewables are taking a larger and larger share. This also helps for carbon neutral energy carriers and buildings, and through electricity or biomass or hydrogen or something else. For transport, there's still quite a few technological issues which have to be solved. But electrification of vehicles is for smaller vehicles anyway is moving fast, and hydrogen is coming, and biofuels, of course, are important. But there's quite a lot of technological development need for the larger transportation sources, ships, trucks, planes. And then we have decarbonization of industry processes, and that is something that in some cases can be, you're going to need a lot of technology to be able to achieve these goals. So in general, what we see is that the tightening of EU climate policies increase the value of CCS and other abatement options in the long term. But the general framework is at best, in a way, technology neutral, where CCS is allowed to compete with other measures. And the policies in the next 2 years will decide which technologies win, basically. So what this also means is that there are 1,978 large emitters of CO2 in Europe. these emit over 100,000 tons each, and some of them several millions. Every single one of the points on these maps has to be mitigated before 2050. It's quite an undertaking, and we can see the segments which industry type they are on the map by the colors. And for some processes in the industry, for example, cement and waste incineration, there are few options beyond CCS to reduce. The nature of their process is just inherently includes emissions of CCS. So, and also both cement and waste energy have the potential for relatively large shares of bio CCS. So they could be necessary to achieve negative emissions. What we see for other types of production processes, there are multiple pathways which include CCS, but also other mitigation technologies. For iron and steel, for example, you have emissions associated with different stages of the current production processes, and CCS can abate some of the stages, but deep emission reductions would require new processes if using CCS. However, it's possible to use hydrogen as well, but also there you would have deep changes in production processes to achieve net zero emissions. And it's unclear which of these pathways would be more cost effective. Chemicals and petrochemicals, they also have a potential for both CCS and hydrogen. Ammonia, for example, which emissions are associated with hydrogen production, can be produced with both steam reforming of natural gas and electrolysis. And it really will depend on costs and policies which will come out of it. Petrochemicals can be produced with chemically recycled feedstocks or biofeedstocks, or electricity and hydrogen for heating, but they are also associated with higher costs than CCS. Refineries have high costs, but they're also high costs for other mitigation methods. So the potential of CCS depends on the politics and the pathways chosen, both by industry and by the EU and countries. And it's hard to know what above the minimum of cement and waste energy is necessary. But you will need deep changes in most industry. Power production is, of course, a very large emission source, but renewable electricity is cheaper to produce than renewables, and power production with CCS could be dependent on policies for bio CCS or for the need for capacity or flexibility. But also there, it's hard to guess. So from these, you have the CCS potential of the EU 28, where you start with a large figure of the CO2 emissions from large sources. And what would be technically possible is due to capture rates and different sizes of sites is, of course, smaller, down to 1.3 billion. And if you look at the industries with high to medium likelihood, you would have which would be cement, waste energy, chemicals, petrochemicals, refineries, and metals. you would have something like 275 million tons of CO2 in a technical potential. For waste energy and cement, which is a high likelihood, you could have 167 tons per year. So hydrogen is, of course, something that is a great uncertainty too. There's a great uncertainty on the level of hydrogen production in the future, which depends on the pathways taken for industry, transport, energy. And also for CCS, it depends on which pathways are taken for production. And there seems to be a clear trend that most analyses see that hydrogen production with CCS is more cost efficient than green hydrogen, but green hydrogen seems to be pointed out by countries and the EU to have a higher potential in the long term. But which of them would win is difficult to tell. This is from the Hydrogen Roadmap Europe, and I love this figure. It says what you need to believe for each of the scenarios, green and blue hydrogen. One of the things you would have to believe for a large-scale green hydrogen is little political acceptance of CCS and drop in costs for electricity and electrolysis. While blue hydrogen, you would believe that steam methane reforming, for example, is more cost efficient, and that CCS is feasible and politically accepted. So there is a wide range of potentials for hydrogen and a wide range of outcomes for the production route. But it's hard to see today. So what the European Green Deal would mean for industries is that the goals and targets say that we're going to a net zero. That means that in 30 years, every emission point has to be mitigated somehow, if possible. If not possible, then compensating volumes must be removed with bio-CCS or natural sinks. So that also means that the prices will increase. You'll be facing higher emission prices to push you out of emissions, and I would think it's timely to consider which abatement options you have, which technologies are available, which could be more competitive in the future. Is there an R&D efforts necessary? Are there infrastructure necessary? Is our industry the ones that's willing and able to pay a higher emission price, or is some other industry better equipped to pass costs on to their consumers? There are a number of pathways, but what we know is that all of these technology developments take a long time. CCS implementation also takes a long time, with perhaps 7 years from the start of planning to start of operations, and that there are very many facilities that would have to implement CCS or something else. So there isn't actually much time in the next 30 years. So for the region, we have a register over all emissions in Europe, and from our register we see that iron and steel production is important, with 5 million tons approximately of emissions. That electricity and heat are a larger share, and that petrochemicals and lime and plaster are smaller shares. For green or blue hydrogen, you could have different production routes for iron and steel. You could either go for the green hydrogen route, which of course would crave a complete reworking of facilities, production of hydrogen, and a lot more electricity usage. If we see the light green path up here, this would be the electricity used today, while the darker green are all the increased electricity needs. While if you went for a blue hydrogen route, you would still need more electricity, but you would need also CCS or transport and storage infrastructure for CO2. So my message here today is that there isn't much time, and that it's about to it's timely to think about what the options are. But CCS works. It's going to be implemented in Norway and other countries. The storage and transport infrastructure is planned to come into place, which can take third-party volumes. And in many cases, it is competitive. And the future will see how much comes out of it. So carbon limits, we can provide help in assessing in early stages what can be done, site-specific analyses, opportunities for use and storage, preliminary design of transport routes, greenhouse gas assessments of the partial or full CCS chain, and review of funding opportunities or incentives. So that was my brief introduction here. Are there any questions?
Let me just add that you may ask, when we have time in each 5-minute slots, you can ask directly to each presenter. And after those 5 minutes, you can send them through chat, and it will be read after all the presentations. So you can choose your way, but maybe now is the best time. So you are encouraged to ask.
Okay, good morning. This is Aditya Sen from Liberty Ostrava. They is one of the major steel producer here. One question to Peter. You are showing there are blue hydrogen and green hydrogen. That means hydrogen from electrolysis process, other hydrogen from natural gas steam reforming. So that means when we go for blue hydrogen, then this CO2, which is generated from hydrogen generation, from that also we need to have a capture to make it completely carbon neutral. And so in the process, obviously, there are a lot of research and is going on how you can use hydrogen in steel iron making process, mainly steel. I'm not talking about steel making, iron making process in blast furnace or in DR plant. So this process is going on. So this is still in the concept stage and some pilot plant process. We have not gone to a commercial application till now. So this is a good, very good option which you have put, because till now we are talking about only electrolysis process. So you are giving a good idea that if the natural gas is available, maybe that can be an option, but I don't know what will be the price. We can compare the price between electricity versus natural gas and carbon capture, because electricity you don't have to carbon capture, and natural gas with carbon capture plus natural gas cost. So do you have any such cost analysis in future that the cost of natural gas expected rise if we go for this with the carbon capture versus the electrolysis way of, that means green versus blue, in any cost comparison you have made or not?
We haven't done any cost comparisons ourselves, but we have reviewed quite a number of them, and it seems as the cost of blue hydrogen with natural gas is much cheaper today, it seems also that the industry is expecting a much or large cost reductions in green hydrogen in the future, and that at some point they might cross. One of the challenges with the green hydrogen, and if we look at the European level, is that you would need massive amounts of electricity to produce this. This also means that either prices of electricity will rise, or you will have a massive amount of windmills and renewable energy projects, which could be limited by space and public acceptance. But it's difficult to see. And we see from Germany's hydrogen strategy that green hydrogen is what they are focusing on. But this is one of the areas with the greatest uncertainty, and we can't really draw any stark conclusions.
Okay, thank you very much.
Any other questions before we move on?
Peter, it's Mike Carpenter from Gas Nova here. Just picking up on that discussion, I mean, you say it's going to require massive amounts of green electricity, because when you look at that pie chart you showed, there's considerable emissions today from power production already. So first you have to have enough renewables to cut those emissions, and then you need even more renewables on top of that before you start producing your green hydrogen.
That is exactly the point. That there's already a massive. I mean, the pathway is we're on the pathway, but the decarbonization of the electricity sector will require quite a lot of renewable energy, and the requirements for hydrogen, if they are green and replace all of the fossil components in all of the industries and some of the transport, will increase this by quite a large share. And it's really it's difficult to see which pathways or how this will end up, but you will need quite a lot, and there could be limitations to what people want to see of renewable energy projects in their backyard.
Thanks.
Björn Erik has a question.
Yes, good morning. Well, this looks like an equation which is very hard to solve, I think. But we're discounting the use of nuclear in order to provide this huge amounts of power. do you have any view here, since we're having this conversation, you know, at the complete exclusion of the use of nuclear energy? So, but do you have a position, or have you even considered producing massive nuclear energy to drive some of these processes?
We have not considered the nuclear, but we've not ruled it out in this. I mean, from an emissions standpoint, nuclear or renewables, we haven't focused on that. But of course, nuclear could, or certainly helps today, and could help in the future. But no, we haven't gone into further detail there. That would be interesting.
Okay, thank you for all the questions and responses. I would like to stop this at this moment because we would like to keep the time schedule, but we will get back in the final part to the rest of the questions. So now I kindly ask Leila to continue with her presentation.
Hello, can you hear me?
Yes, perfectly.
Yes, and
Very good. And do you see the slides? Do you see the presentation?
Yes, we do. Thanks.
Very good. Thank you very much. Good morning, everybody. I'm going to share this presentation with my colleague, Dr. Audun Drogaset, who is an environmental expert. Audun, are you there? And could you also try your line now? Let's say hi to everybody.
Yeah. Hello, everyone. Thank you for the introduction, Leila.
Perfect.
Everyone can hear me?
Yes, that's great. Thank you. Thanks very much. So Audun is an environmental expert, and I myself am a chemical engineer by background. We both work at Technology Center Mongstad, or TCM, and together we present today CCS, what turns grey hydrogen blue. And our focus in this presentation will be the CC part of CCS, meaning carbon capture, and we will talk about how to deploy carbon capture at industrial scale safely and in a timely manner. Now, to decarbonize many industries, CCS is essential, as was also mentioned by Peter. Examples are electrification of transport system, energy supply, and use of hydrogen as a carbon-free fuel. In all of these, CCS will play the central role. Here, let's focus on hydrogen as a carbon-free fuel. We have prepared a quick cheat sheet for you, and I'll go through the cheat sheet. Today, 95% of world's hydrogen is derived from natural gas or coal, let's say from fossil fuel, basically. This causes between 9 to 12 tons of CO2 per ton of hydrogen produced. To turn grey hydrogen blue, or in other terms, to decarbonize grey hydrogen and make it low carbon fuel, CCS is a must. CCUS reduces carbon footprint of grey hydrogen by about 55 to 90%, and having this range in mind is very important. Can we really call it blue hydrogen if we only partially remove the CO2? Possibly not. Now, when blue hydrogen is produced through fossil fuel reforming, the CO2 footprint will basically depend on type of capture process that is chosen and the capture rate. In other terms, the fraction of total carbon that is removed and captured. Now, in the block diagram here below, you see hydrogen production through reformation of natural gas, a steam reformation of natural gas. And you see several points in the process that CO2 can be captured and removed. It happens a lot that people focus on easy to capture stream, meaning after the shift reaction. And most often the stream that is hardest to capture the CO2 from is ignored. And that more difficult part is the flue gas from the heating process. And if you ignore to capture from the flue gas stream, you have left about 40% of the total CO2 emissions, and the produced hydrogen cannot really be called carbon-free. Now, let's ask a very critical question. Does blue hydrogen make sense? And the answer is it does, but if only does if CCS is efficiently done. Now, let's start the capture thinking very simple. Your industry currently emits a considerable amount of carbon dioxide. Let's imagine that scenario. And it might be hydrogen production, steel manufacturing, etc., that you want to integrate carbon capture technology to. There are various technologies out there in the market to choose from, and what you need to do is to set up a systematic technology assessment procedure. And first step to select a technology is to assess the type of flue gas that you're emitting, how much CO2 it contains, what impurities it has, what is the pressure of the flue gas. These are the most basic but the most important questions that must be addressed at the first step. So characterization of the flue gas must be done carefully before you bind your project to any specific technology. It means your work starts at your facility. When that is done, you start the technology selection process and go through the feasibility study and risk assessment. By now, you have most likely listed a couple of technologies, and you start asking the suppliers of technology questions like, what CO2 capture rate is feasible? How does energy and heat requirements look like? You ask about CapEx and OpEx, environmental impact assessment, etc. And you need to look into integration aspects too. Like, do you have excess heat at your facility? How much space do you have available? Is your upstream process very dynamic? And if so, how does it impact the various technologies that you have listed? So all these systematic questions must be put to technology suppliers before you sanction deployment at a scale. At TCM, we have a lot of experience with such assessment procedures for carbon capture technologies, and we can help you with that through our advisory division. Okay. Now, the main benefit of a systematic technology assessment procedure is that you will crunch the risk curve and avoid pitfalls through the life of your project. This graph tries to visualize this concept. Because CCS does not have a long industrial history, it is natural that there are risks associated with it. But majority of risks are quantifiable and manageable, and this is the main message of this presentation. If you identify the risks appropriately, you can avoid or mitigate them. So through technology qualification, you can manage your CapEx and OpEx. One example is choosing the right chemical solvent for capture, which if may I ask everybody to mute their microphones, please? Thank you very much. So one example is choosing the right chemical solvent for carbon capture, which if you don't, it will probably degrade. The solvent is going to degrade, the chemical is going to degrade, and it will be wasted. And you must frequently replace it, which is not only an unsustainable practice, but also significantly increases the OpEx of your project. There are also regulatory issues to be aware of. Regulators and authorities are developing stricter environmental requirements, and it is important to choose a technology concept with minimum environmental impact for example, risk of secondary emissions that Audun is going to focus on after I'm done with my part. In summary, you need to use the best knowledge and risk assessment solutions available to you to make informed risk-based decisions through the whole life cycle of your operations. And luckily, many of the solutions and lots of knowledge is available today, and you hear about it through the presentations that our colleagues have prepared for today's webinar. So now imagine you're an industry that does not know much about CCS, and imagine that you have not built a concrete and systematic architecture for your CCS project, basically to minimize risks that we showed in the previous slides. The result can be bad surprises and pitfalls. We've listed some of the observed pitfalls. These are our observations in this slide, and some of these items we have learned after operating our carbon capture facility for 8 years. For example, a chosen technology may not match the flue gas specifications for your specific application, or the actual operating environment is not tested, or models and prediction tools are lacking, or when they are available, they're poorly validated due to lack of operational data. And the consequence is going to be obvious. You face budget overruns, poor carbon capture efficiency, and poor reliability and frequent downtime of your facility. Now, with all that background, we can say that Technology Center Mongstad, or TCM, that you see in this picture, is the major tool in the Norwegian government's toolbox to de-risk carbon capture technologies. In Norway, apart from funding commitments, the government has been involved in the technological development of CCS to reduce technical risks and uncertainties. That is achieved through Gassnova, who are a state-owned company and who oversee CCS efforts in Norway. We have a presentation by Gassnova afterwards. Gassnova, on behalf of the government, owns 77% of TCM, and the rest is equally shared between the 3 industrial partners, meaning Equinor, Shell, and Total. So TCM was launched in 2012. Our facility is in the west coast of Norway, and we are neighbors to the Equinor Mongstad refinery. You see the refinery on the left of this picture. Also, in our vicinity, there is a natural gas combined cycle heat and power plant. The power plant is this white building that you see in the right corner of the picture. In the middle, between the yellow, red and white arrows, you see TCM. So the unique location of TCM next to a refinery and also next to a power plant provides interesting opportunities in terms of flue gases that we treat. TCM is designed to treat both the refinery flue gas and the power plant flue gas. And at TCM, there are 2 CO2 capture facilities. The plant in the front is a chilled ammonia plant, and to the back of it, there is an amine plant. These 2 plants together have the capacity of up to 100,000 tons of CO2 per year. And our capture both of the plants are fully instrumented. This gives us complete control of what enters and what leaves the plant. And this very tight monitoring of what comes and what exits the battery limits of our facility has given us deep insight into environmental aspects of carbon capture technologies. We also developed an area of demonstration of novel or alternative carbon capture technologies. This is an exciting development that I speak about in my in this slide and the last slide, basically. So this is an area of about the area that you see in the right side of the picture is an area that we developed recently. It's about 700 square meters. And we are going to start demonstrating 2nd generation or technologies that are alternative to chilled ammonia and amine technologies from autumn 2020 it was the plan, but I think we start early next year now. There's a slight change in plan now. And this new site that you see in the picture, you see the pavement here, we are able to capture around 20 to 50 tons of CO2 per day in this new site, and it is designed for technologies like membranes, adsorption, alternative contactors, and basically anything alternative to conventional technology. And with that, I pass it over to you, Arun.
Yeah. Thank you, Leila. So our aims to implement carbon capture is to solve a global problem. And it's important that when we do this, we are safeguarding our local environment. And for my slides here, I will focus on the use of amine capture technology. So it's important that we make sure that we have clean drinking water and the air we breathe is clean and we don't impact the surrounding earth. And we do have the tools to achieve this and implement CCS. And there are a couple of key steps to the road to success. If you go to the next slide, Leila. So the first and arguably one of the most important steps is that we reach a common understanding between us, the plant owners and the one who operate the plant, the public that shares the local area with us. So I shared a picture here of my hometown, and the regulators. So the knowledge needs to be shared amongst the participants. The plant owner need to ensure the public that they will run the plant safely, and the regulators also need to ensure the plant owner and the public that the plant can reach their goals of capture and that they will do this safely and protect the local environment. So if you go to the next slide, it's important that we understand the impact of emissions to air, talking about amine emissions. And for understanding the potential impact, it's important that we start at home, as Leila said, that you know your local conditions. Because the local conditions at your site affect what happens in the air. Are there other industries in the vicinity? What is the air quality? And other pollutants from other industries could affect what happens to your emissions in the air. And then also it's important to look at the local water. Is this drinking water? Is there a lot of biological activity? And the local earth. So is there groundwater sources, for example, agriculture? Because if you emit amines, there are other industries that do pollute amines, for example, agriculture. So it's important that you have a thorough background study, so to understand your local conditions. You can find seasonal variation that during winter and summertime, there are different occurrences of natural amines in the water environment, and likewise the surrounding earth. And also the seasonal variation in the air change the degradation of amines. And then when you know your local environment, you will be better able to make sure that you have safe emission limits and plan how you must monitor your environment in order to protect the public. So the work you do early, it helps put up adequate barriers to protect your workers and the local environment. So if you go to the next slide, Leila. So, and all of this starts off but asking the question, what happens to your emissions? And there are a lot of key steps here that we at TCM has a lot of knowledge, especially for following up emissions. How do we reduce the emissions? How do we adequately monitoring them? So we have a lot of learnings here. And also looking at how they are dispersed in the atmosphere. And then what happens in the atmosphere, because the amines we emit, they can react with the light in the atmosphere and other gaseous components in the atmosphere in photochemical reactions and generate new products. And some of these products, depending on the amine technology you select, could produce some toxic compounds. And you need to have this in mind when you select your technology. Think about the entire lifetime. And then you can see where does these pollutants end up in the environment. And then you can also plan how to follow up and under what conditions you need to put safe limits to emissions. So, and these steps sort of work in reverse when you are early in the project. You see what is in my environment. Are there agriculture that already puts amines into the environment? What is the seasonal variation? Your atmospheric monitoring tells you what type of atmosphere is surrounding my plant and how will that affect the atmospheric chemistry. And then your dispersion modeling gives you input into how to design your plant. How high must the stack be? And all of this gives you input to the safe limits, and the safe emission limits you get determines what type of technology you have to implement in order to follow up these emissions and how to make sure you have adequate sampling and high quality in your sampling. That was very briefly on some environmental topics. And yeah, back to you, Leila.
Thank you very much. Are there any questions for myself and for Audun? No, apparently not. Everything has been clear. So with that, we pass it over to Mike Carpenter. Mike, please.
Okay, can you hear me?
Perfectly, yes.
Yes.
And you can see my presentation?
Not yet, actually. It's a black screen, Mike. At least for me.
Is that better?
A lot.
Excellent.
Yeah,
Okay.
now perfect. Thanks.
Thank you for the invitation to present. I'm going to talk about options for what to do with the carbon dioxide, having captured it and separated it from a process stream or waste stream flue gas. And what we're aiming to do here is reduce the carbon dioxide going into the atmosphere. And what we've been doing for the last 100 years, while we've been using energy from oil, gas and coal, is taking hydrocarbons out of the rocks, burning them, and the carbon dioxide waste gas has been going into the atmosphere. So the Earth has a natural carbon cycle where carbon is moving between the atmosphere, the biosphere and the geosphere through natural processes. And by burning oil, coal and gas, we've been accelerating the output of carbon from the rocks into the atmosphere. So carbon storage is a process to try and reverse this, to help rebalance the natural carbon cycle by taking carbon dioxide that is on its way out to the atmosphere and and recycling it back into the rocks. So taking CO2 from the fast carbon cycle, the atmosphere, and putting it back into the slow carbon cycle in the rocks. How do we do this? Well, the process is actually very similar to how we get oil and gas out of the rocks. We inject CO2 in liquid form, in a dense form, into the subsurface. Here we see 3 pictures of wellheads. 2 of these wellheads are producing oil and 1 is injecting CO2. And it's not immediately obvious which is which. We're using the same technology, the same kind of well structures. And the one on the left is the CO2 injection well. This is from an enhanced oil recovery project in the US. This has been injecting CO2 for many years. It's not dangerous, and this technology has a much longer track record than most people are aware of. So it's about moving fluids into the subsurface in a very similar way to that we extract fluids from the subsurface. Now, how to pay for this? Obviously, it comes with a cost. You have to compress the CO2, you have to pump it, you have to drill multiple wells, and you have to monitor to make sure that you're doing this in a safe way. And it also requires exploration, similar to oil and gas exploration, to find the geological structures that are suitable for storing the CO2. This can be onshore, it can be offshore. The costs for CO2 storage are generally lower than the costs for CO2 capture, but this depends on what kind of waste stream the CO2 is coming from. But what the experience we have in Norway is that it takes a long time and it does cost money to explore for these kind of geological sites and to operate them. So this is where the idea of a public-private partnership comes in, because carbon capture and storage is something that national governments, the European Commission want to achieve. It's something that industry also wants to achieve. And it requires financial support from many sources in order to put together a funding jigsaw puzzle and an organizational jigsaw puzzle to make this happen. So on the public side, there's funding available at an EU level, and there's funding available sometimes at a member state level. So at the European level, you have the Innovation Fund, which is now opened up for applications for CCS projects. That is in the process of happening this year. And that's worth looking at. The European Central Bank has announced that it's modified its position on CCS and it's now willing to lend funds for CCS projects. So that's debt financing. National grants, like the Norway grants, have supported a lot of CO2 storage research in the Czech Republic, for example, and the European Bank for Reconstruction and Development. They also provide infrastructure debt financing. Member state discretionary funding. Norway is not a member state, but we're part of the European Economic Area, and we're fortunate that the government here has provided funding for doing studies for CO2 storage and CO2 capture, like the TCM. And I'm not sure what's available in the Czech Republic, but obviously that's something for industry to explore. On the private side, if you start doing CCS, then you avoid paying for a quota within the emission trading scheme. So whatever the current price or how you predict the future price of emission trading scheme quota, then that can be an incentive for doing CCS, because that will be a cost that you avoid in the future. And then the drilling the wells, operating a CO2 storage site, maybe operating a CO2 transport pipeline, that will also cost money. You can imagine a private company operating those facilities, and they need to take a fee in order to get a return on their investment. So that is also needs to be a business case that's feasible for them. And in Norway, again, we're seeing the Northern Lights partnership with Shell, Total and Equinor creating a business model for that. And the cost of that storage fee is also something that the CO2 emitter needs to price into their model. So this is a industry that's really at a very beginning. Everyone's trying to find a business model that works, but with the mixture of funding streams that we see here, we think we can see a way forwards to a commercial model in the future. But the money's one thing. The other part is the organizational coordination, because this is really complicated. It doesn't need to be super complicated, but the fact is there's a lot of actors in the picture if you want to get a CCS project off the ground in Europe today. So it's good to start coordination early. You have politics at the top here, the EU level politics, the national politics. And then within a country, you have different ministries typically looking after different parts of the CO2 value chain. You might have an environmental ministry looking after air pollution, groundwater pollution, which is has an impact on the licensing for the capture and the storage. And then you'll have laws and regulations down to the left there, EU directives, national laws, and then the regulatory bodies within a country may not necessarily be coordinated to start with. They may not be familiar with CCS as a technological solution or carbon storage, and it's important to get them on the same page as early as possible. And then very importantly, you have the business operators that want to find a solution for their carbon emissions. But in order to make something happen, somebody has to push a project forwards. In Norway, this has been industry. It's been the capture plants and the storage operators. And the government has asked them to take the lead and provide the initiative to get a project going. But that requires a certain level of commitment, and it's important that somebody is taking the lead here and asking others to coordinate their approach. Very briefly, the experience from Norway. The government has asked the capture, transport and storage operators to take the lead. They've provided some funding for engineering studies, and that's been organised by the Ministry of Petroleum and Energy. And they've given the task to Gassnova, where I work, to help coordinate things. But it's up to the companies themselves to apply for licenses and permits and take care that they are in accordance with the national regulations. And then in Norway, when a government wants to spend public money, there's a very formal quality assurance process before the project goes to Parliament for the final investment decision. That quality assurance process is just closing out this month in June, and we're expecting the new project in Norway to go to Parliament for an investment decision in the autumn. So again, the coordination has taken a number of years. but we're seeing the fruits of that now. There's a little bit of information about how GasNova has done that coordination. I'm happy to answer any questions on that. And then I just want to finish by highlighting the collaboration between Czech Republic and Norway already when it comes to CO2 storage. The Czech Geological Survey has done a lot of work mapping CO2 storage potential in Czech Republic. And we're lucky to have Vlit Hladík on the call today. He's been coordinating a lot of that research at the Czech Geological Survey, and he's also available to answer any questions. Thank you very much.
Thank you. Is there any question for Mike? No questions? Okay. Thank you very much, Mike. Thank you.
Thank you.
So with that, we move to the next presenter. He is Albert van der Noot from DNVGL, and I appreciate, Albert, if you introduce yourself before you start. Thank you very much.
Yes, my name is Albert van der Noot, and I hope you can hear me and can also see my my presentation.
Yes, it's very
Yes. Okay, perfect. So I work for DNVGL, a Norwegian company, but I work in our office in the Netherlands, where I'm responsible of the hydrogen activities that we do in our region, ranging from most of Europe, a little bit to Asia, and also the Middle East. And what I want to do to tell you today is some aspects of the hydrogen value chain. I think in the previous presentations we've heard a lot already about the role of CCS and hydrogen, and I will expand a bit more on that and also talk a bit more about the transportation and the end use of the hydrogen. But before doing that, let me see, yes. A few words on our company. DNVGL is a global quality assurance and risk management company. We are active in the maritime sector, where we started, oil and gas, offshore, also in CCS, of course, and in the power sector as well. And in this sector, we offer verification and certification services and also advisory services. And our purpose is to safeguard life, property and the environment. And as much of our business is in the energy sector, it is of importance, of course, that we are in this energy transition and what will be the role of this energy transition to our business. And for that, I think we all agree that we have to do something about our CO2 emissions. And we agreed in Paris Agreement that we want to limit the heating of the atmosphere to 1.5 degrees, preferably, and that well, calls for action. Already mentioned by Peter, we do not have a lot of time left, and I think there's not one solution that well will enable us to meet these efforts. And in this whole spectrum, hydrogen and also CCS plays an important role. But as already mentioned, it is not the only solution. Talking a bit on hydrogen, and we've talked about the CO2 emissions from several industries. Well, one of the industries that produces a lot of hydrogen nowadays is the refinery, the ammonia production, and also the methanol production. Those are actually also the 3 largest industries that use a lot of hydrogen nowadays. Global demand up to 400 exajoule. For pure hydrogen demand, it's roughly 10 exajoule, and together they emit well, over 800 megatons of CO2 per year, which is a lot. And if we can limit these emissions, we can contribute to our CO2 emission goals, and on the other hand also still produce different chemicals, and because these industries also produce chemicals or products that can be used in society. For example, the ammonia is used for production of fertilizers, refineries, of course, for different fuels, and the same holds for methanol. And we will still need those products in the future. So hydrogen nowadays, demand is large in different sectors, but mainly as a feedstock. And if you look at the hydrogen value chain, we've already discussed the production of hydrogen. There are different colors labeled to the hydrogen. In this future, we want to be carbon neutral, which means that either on the top, we produce hydrogen from SMR, or from gas via SMRs, or from ATRs as well, where we capture the CO2 and store the CO2. It's called blue hydrogen. The other route is from electrolysis, and as already mentioned, you need a lot of green electricity for that. You produce hydrogen from water with electricity. So those are the two primary ways of producing hydrogen. But once you've produced the hydrogen, you need also to transport it to the end users that in the end use this hydrogen. And there are different routes available there as well. And that depends on the quantity that you want to transport, and also the distance that you want to transport it. Currently, roughly 85% of all the hydrogen that is produced is consumed on site. So you go back to the previous slide. If you have a refinery, often there is an SMR available that produces the hydrogen, which is used for the desulfurization of the crude oil products. So most of the hydrogen is consumed on site. 15% is transported via trucks or via pipelines, and a very small share is traded freely. And there I also mentioned the two main routes of transporting hydrogen. It's either via trucks in compressed form, or via pipelines, where the capacity is of course a bit bigger. There's a lot of activity also going on to research into transport of hydrogen via shipping, where the liquid form of hydrogen, liquid hydrogen, is considered, or other liquid forms in the form of ammonia, or using a liquid organic carrier. And then, of course, the storage of hydrogen is also important. And that brings me to the next slide, which looks at the role of power to gas in enhancing the flexibility. So the end game, I think, is to have green electricity, or green energy at least, produced from either the sun or from the wind. And if you have this electricity and you can use it in the different sectors, which are listed here at the bottom, you should of course do that. But the main difficulty with electricity is that it's very hard to store in large quantities over longer periods of time. And if you want to use the electricity for example, heating the domestic environment, the houses, you will need more in the winter and less in the summer. So you need to balance that. And with electricity, that's quite difficult, especially if this electricity is produced on moments when the wind is blowing or the sun is shining, which is not necessarily the moment that the electricity is needed in the different sectors. And there the hydrogen comes in handy, because if you convert the electrons to molecules, the big advantage of that is that you can store them more easily, and also transport them in larger capacities via gas pipelines. So if you could convert the hydrogen into the electricity into hydrogen, you could also use that in the different sectors. And here then the sectors that we mainly look at are the residential area for heating, also heating in industry, industrial use as a feedstock, mobility, and electricity generation as well. Electricity generation is important. Once again, if the wind is not blowing, there's a lot of electricity need, then electricity generation via gas-fired power plants or hydrogen-fired power plants is a possible option to balance the electricity grid. So hydrogen is, in this case, an energy carrier and can be used in the different value chains as well. I put in this slide before knowing that this was already mentioned in the previous presentation, but nowadays we produce hydrogen, as said, mainly from natural gas. We see a transition towards blue hydrogen, where we convert the natural gas into hydrogen and capture the CO2 and store it underground. But in the end, we look at the green hydrogen production. And here on the timeline, it says 2050. Well, there are different scenarios, of course, on how realistic this is. Depends on the amount of electricity that we have, but also depends on the different infrastructures that we have. So what we see, at least in the Netherlands, and I think in more countries around the North Sea, is that there are quite large ambitions for offshore wind, and the wind farms are placed further and further away from the coast. And at a certain moment in time, it becomes more attractive to transport the energy in the form of hydrogen compared to the cables towards these offshore wind farms. And that's also onshore one of the cases, and that's shown here. This is an example from the Netherlands. As you might know, in the Netherlands, we have a lot of natural gas in the northern part. If you can see my cursor here, in this area, there's a large gas field which will now be abandoned, which means that a lot of the natural gas pipelines become available. And in the Netherlands, we use natural gas for heating. There's capacity available from the natural gas infrastructure. And on the other hand, we are planning a lot of wind farms on the North Sea. And the TSO for the electricity, TenneT in our case, has quite some difficulties of connecting all these wind farms to the electricity grid. So extending the electricity high voltage grid in the Netherlands, and also the same holds for Germany, for example, is quite difficult because there's a resistance of building new overhead cables. While on the other hand, there's an underground gas infrastructure which will become available. And that leads to the idea of converting part of this grid to a hydrogen grid. And as said, this is the example from the Netherlands, but the same holds for Germany as well. And what we want to do in the Netherlands is connect the large industry clusters. We have 5 of them where there's methanol production here in the north. Here are the refineries in Rotterdam and in Zeeland. Here's steel production near Amsterdam, and ammonia production near in the southern part. And we want to connect these different clusters with a hydrogen backbone, which transports 100% hydrogen, or nearly 100%. So reuse the existing grid, preventing extensions of the electricity grid, and in the meantime also producing a lot of hydrogen via electrolyzers at these sites as well. That's the idea. And there hydrogen plays an important role of balancing these different value chains. If you look at reusing the infrastructure for hydrogen, the gas infrastructure, there's been a lot of research going on. In the past, we conducted a large European project which is called Naturally, where we looked at using the existing gas infrastructure for hydrogen, which ended somewhere 2010. And after that, as DNVGL, we set up a joint industry project, which is called HyReady, where we took all the learnings from different research projects and made practical guidelines on how to convert gas infrastructures to hydrogen. And mainly looking at the blend of hydrogen and natural gas. So we did that for the transmission parts, but also for the distribution grids. And we looked at the end user appliances and the compressor stations as well. So for each of the components in this grid, we made guidelines on how much hydrogen can they easily afford without much consequences, and when will be, and there will be consequences, what would be mitigating actions to keep the consequences within the limits that are acceptable. And that's also, of course, also important. What are the risks associated with converting infrastructures to other gases? And in the past, we've done quite some experiments in our site in the UK. We have a remote site where we can do large-scale experiments. We did those experiments, as a matter of fact, also for CCUS, CO2 pipelines. But this is an example on the right of a hydrogen pipeline. This section is 1.5 meters, and it was a 60 bar hydrogen pipeline. And we looked at what happens if you would rupture the pipeline. Well, a fire was created, and we did the measurements and learned that the effects of this fire were comparable to gas fires of the same power. So proving the safety case is important if you want to reuse the infrastructure. Another part of research that we've done recently is if you switch from natural gas for heating to hydrogen, you need to adapt your burner systems. And this holds for industry, for large-scale burners, but also for the small ones that we typically use in the Netherlands for heating our houses. But it could be also extended to the ones used in power generation. What is known, of course, is that if you burn hydrogen, it burns much quicker than natural gas. So you need to change the burner system. And if you add a percentage of hydrogen, you can solve this by well, changing the control mechanism of the burner. At a certain stage, you might also need to replace the burner system itself. But in principle, it should be fairly easy to adapt existing burners for the use of natural gas and hydrogen. And here at the bottom, you see the experiments that we've done from natural gas, 100% up to 100% of hydrogen on the right, with all kinds of mixtures in between. So this is ongoing research, and as a matter of fact, in the Netherlands, it is of importance to see if we can also adapt the end users and see if they can accommodate more hydrogen and also decarbonize in that sense. Another pilot that we did near Rotterdam is a hydrogen production unit, a very small one, located here in these containers, where we produce hydrogen from electricity via an electrolysis, and we transport this hydrogen via a pipeline, which is not visible on this picture, of course, to this apartment building at the end, at the back of the picture. And in this apartment building, there are a number of boilers that use pure hydrogen for heating, and it's well, ongoing demonstration project for a number of years. In the first phase, we produce the hydrogen converted into methane. That's also a possibility, where you use preferably captured CO2 to produce methane again from hydrogen. And then you can use it in existing boilers and infrastructures as well. This is a very small project. A larger project is executed in the UK, where near Leeds, the H21 project is currently executed. The idea is to convert a number of cities in the northern part of England to hydrogen for heating. Also, this hydrogen is produced via SMR combined with CCS, and then transported via pipeline systems to the cities. And in the cities, it's used in the households for heating. And once again, here we were involved in this project mainly to prove the safety case. So we've built a number of houses on the same remote location I was mentioning before. And we did experiments on leakages in the houses, gas buildup of the hydrogen buildup in the houses to see if there are dangerous concentrations and what well, countermeasures you can take. We did different experiments on the flow of hydrogen through the soil on large-scale releases for 8 bars and lower. The effects of explosions here at the middle, and also the ignition potential. hydrogen ignites more easily than natural gas, but what kind of sources would be dangerous, so that you can ignite a dangerous concentration of hydrogen in houses or near pipeline systems. So that's ongoing work that we do in the UK. And with that, I hope that I've given some extra information on the role of hydrogen in different aspects of the value chain. So it's, I think, important not only to look at the production side, but if you want to optimize the system, you need to look at what is available. If there are pipelines available, you can reuse them, for example, or you would need to improve your electricity system, which also means a lot of extra costs. And I think, well, that's what I wanted to talk about today. So if there are any questions, I will be happy to answer them.
Thank you very much, Albert. Any questions? I have one question for you, Albert. What are the potential business cases for methanation of hydrogen in the future?
The potential business case. Well, methanation is interesting if you have a distribution grid with a lot of end users that are too costly to convert directly into hydrogen. The downside of methanation is that you again burn methane at the end, producing CO2, which is probably emitted to the atmosphere. But if this CO2 was which was used in the methanation project is from the short cycle, as mentioned by Mike, then that should not really be a problem. But the main business case is if you can that you use methanation if there are a lot of small end users that are too costly to convert directly to other carbon-free solutions.
Thank you. Thanks very much. Any other questions? Yeah.
Albert, this is Aditya Sen from Liberty Ostrava. What I have understood from you that in future the trend is changing the natural gas network to hydrogen network. Is it correct? That means the same pipe, same network going natural gas to end users that can be transferred to hydrogen.
Yeah, that's in a number of countries in Europe. That is important research of ongoing projects. So we have an asset, which is the natural gas infrastructure, which is connected to a lot of end users, which will be well depleted in the future because we are not going to use natural gas anymore in the Netherlands. So the alternative is to reinforce the electricity infrastructure, which is very costly, and which would mean that we need to replace all the end users as well. So the idea is to reuse the existing gas grid and adapt the end users to hydrogen. But again, as said, that there's not one solution for all. For example, if you look in Norway, I think not many houses are connected to a gas grid. So you need to look at the local circumstances to see if this reconversion of existing infrastructure is an interesting option.
Okay, thank you.
Any other questions? Thank you very much, Albert. Now I would like to pass it to Gabrielle. Go ahead, Gabrielle, please.
Thank you. Thank you, Albert, and thank you all presenters for in-depth presentations. It was the last one from Norwegian and Dutch presentations, but we still have one remaining from the very beginning, and it is the introduction to Moravian Silesian region from hydrogen perspective. So I kindly ask Mr. Daniel Minařík from Technical University and from above all from the city of Ostrava of the topic. Yeah, I see him here, so thank you very much, and I'll pass the word to you, Daniel. Welcome.
Yeah. Hello. Greetings from Ostrava to the Norway or Dutch, or also to the colleagues in the other parts of Czech Republic. Also to any Ostrava companies who is working here. Thanks for a short introduction. Maybe just several words about the Ostrava or about the motivation to joining to whole agenda around let's say green technology, hydrogen technology, and also CCS technology. Ostrava is historically oriented to the industrial Ostrava is a historically industrial city, it's causing many problematics, not just relate to, let's say, well-being in the city, but also produce problematics with, let's say, carbon transition and all kind of these problems. City of Ostrava, or whole region, what is representing by the Moravian Silesian region, who is let's say regional government. Looking for some new solution for that transition, and what is a let's say very good constellation in this time is a very close and very close cooperation between the city, what is a, let's say, of course, capital of Moravian Silesian region, with Moravian Silesian government in that area. I want to, let's say, inform you about two kinds of let's say motivation or project orientation of City of Ostrava or Moravian Silesian region, as you want. City of Ostrava wants to be, let's say, headliner in the area of whole Czech Republic or close area of V4 countries in a hydrogen. Why Ostrava? Because historically, as I said, we are oriented to industry, heavy industry, what is big producer of CO2, but also have a capacity for producing of hydrogen or synthetic gas, what could be source of hydrogen. For Ostrava, as the city is today the most harmful situation with air quality. That problematics during 20 years going rapidly up. So quality of air is not comparable with situation between 30 years ago after Velvet Revolution, if you want. But still we have a problem in this area. So one tool what is control directly in the city is public transport, of course. The same situation is on the level of Moravian Silesian region. So we decided, city and the region decide for close cooperation in the public transport and the application of hydrogen technologies as the next fuel for the future. In this level, region and a city has a, let's say, motivation to stimulate and let's say motivate all stakeholders. What is settled on the region or city area for collaboration. There is one kind of support, and of course, city and the region wants to be direct apply of hydrogen technologies in the city transport. Today, currently running the project for building up first public filling station or hydrogen filling station, mainly for public transport. But sorry, because this is a let's say application what has of course has a commercial impact, and let's say it's a project oriented also for profit. Today, what is a stage of this project today? We are choosing of company who will be design this filling station for our city transport company purposes, and for not just the filling local buses, let's say, but also for filling regional transport buses operated by Moravia and Silesian region. This is one way how to city and also region wants to support all activity around application of green technology, because investor of that filling station is a practically city. So a question about let's say future producing of hydrogen is a crucial also for city, because it's not possible to let's say using of gray or standard made hydrogen from the stream reforming. City of Ostrava or City Transport Company has a plan for next stage of this project, including of course local production of hydrogen from renewables, but amounts of hydrogen what we need, we're talking about let's say 1 ton per day for our regional and city buses. So it's not possible to cover just from the renewables. So combination of any other hydrogen production technologies could be also applied. So CCS is also very interesting for us or for my colleagues who are practically responsible for that project or realizations. So thanks Norway partners or for very good presentation oriented to not just for technical problematics, but also problematics related to the financing this kind of huge project. Anyway, City of Ostrava has very good contacts with Norway embassy in Prague. We've prepared and also collaborate in several project with embassy and any other partners from Norway, what was oriented to let's say smart cities agenda, but from our view is time for looking for some new partners who is oriented for hydrogen technologies and for any next step of collaboration, not just with the city, but also with any other companies in a region who has some motivation to change their let's say business model and switch to the hydrogen or green technology, if you want. So please do not hesitate to contact me as a city energy manager who is responsible for, let's say, strategy of a city in this area of energy and CO2 footprint for next discussion, not just on the technical themes, but also from the view of financing and any other support of city to this kind of projects. Yeah, thanks.
Thank you, Daniel. Now I was supposed to read the questions in chat, which is a very easy task because there is none. But this is pretty typical for Czech conferences. There are never any questions. The main communication is during the lunch breaks, which is the communication that we cannot afford today, unfortunately, but still I think it's worth it. So maybe I will try to summarize a bit. On the Czech side, there are various companies, mostly heavy industry or energy sector. The experience in CCUS and hydrogen differs in each company, but as majority of the companies admitted in their profiles, both are pretty theoretical or basic. I encourage all companies to send their questions now or after the webinar, probably after the webinar, if they see some potential for any cooperation with Norwegian partners. You may address each other directly after the webinar, of course. You have the contacts within the profiles. Nevertheless, we will be glad to get the feedback on such a progress to trace it a bit. And obviously, all information you provide us will be shared with TCM. If needed, we offer assistance. Our role, speaking as a B partner representative, is to identify potential source of financing, particularly from European, but perhaps also Czech or Norwegian supporting programs, as it was said. And from this point of view, I would like to discuss it in more details with the colleagues who presented it before me. So there definitely will be some future conversation, I hope. But we are, as I said, we are prepared to assist eventual projects built on new CCUS technologies tested and applied by companies, knowing that the external funding will be necessary. Several other organizations from the region who might be of help take part in this webinar. For example, it's Moravian Silesian Energy Center or 2 EU research projects led by regional universities. And you already heard Daniel to present the position of Ostrava city and a bit summarizing also the regional perspective. There might be also some opportunity for technology cooperation among yourselves as you represent specific sectors. So we will see. It's up to you, of course. For this moment, it's everything from my part. I don't have more to say. Oh well, maybe I'll check. I'm checking the chat again. So I will pass the word to Leila once more to complement me. But before I do this, I read the conversation in chat. sorry, the question in chat. It is the question from Mr. Radek Yerku from 7 Energy. What will be the breaking point for getting hydrogen generally into the money from the market point of view, meaning grey hydrogen is too expensive for using? How to make it cheaper for public to jump before natural gas? There is not mentioned who shall respond, but would you? Some of the presenters?
Any volunteers from Norway and from the Netherlands? Maybe Peter or Albert? This is a question that can be best answered by the two of you. Peter Brown and Albert?
I don't have an answer to that on a standing foot of where the breaking point is, but it will generally be based on the electricity prices and the emission prices, and the trade-off between them, and of course gas prices. I don't know if DNVGL has more insight.
I can comment on this. My name is Jørgen, so I work in DNVGL as well. In terms of sort of when the breaking point is, I think there's one question when sort of blue hydrogen becomes cost competitive to green hydrogen. And currently sort of the CO2 capture price for hydrogen would be in the range of $50 per ton. So when you see a CO2 price extending above $50 per ton, you would make that sort of cost competitive. The other question I think that is being raised is also sort of when is, let's say, the competition between green and blue hydrogen. And that's the question with regards to both electricity prices. And one of the assumptions that are being made is that when you get greater penetration of renewables, you will also have access to surplus electricity, and that electricity will be free or at least very low cost. So based on those assumptions, and in terms of how many hours a year you might have access to that type of electricity, you can make some predictions on the price of green hydrogen. And taking those assumptions into account, you might say a sort of cost competitiveness of green hydrogen towards blue hydrogen and post 2030. But that will typically be based on an operating model where you're only producing a certain numbers per year. So if you're producing, let's say, more continuously, then the operating model will mean that you also need to use, let's say, higher electricity prices. But the short answer here is that currently hydrogen produced either blue or green is not cost competitive with hydrogen produced from gas itself. So there needs to be an incentive to incentivize either green hydrogen or blue hydrogen through CCS. Would you like to add to that, Albert, if you're still online?
I think that's also the answer that I would give.
Thank you very much. Gabriela, there's a raised hand.
Yeah, maybe some more questions before we finish.
I think Roman Brenneblom has a question.
Yeah. Laila, it's more of a comment on the hydrogen economy from, let's say, a research or applied research institute point of view. I think one of the things that can affect is essentially economy of the scale. As I have mentioned before, it's either the CCS that gets cheaper, or let's say the renewable energy that gets a lot cheaper, that would allow to produce the hydrogen at a lower cost. But we're still going to be facing the infrastructure rollout issue that, for example, electrical cars didn't have, because electricity is available everywhere. It also can be a breakthrough technology that is basically bringing disturbance to the market by allowing to produce a resource with previously unknown tech that makes it cheap and efficient. But it's also a gradual transition, and there is a UK example where you start mixing the hydrogen into existing gas infrastructure and ship the mixture of, say, methane or whatever gas you use in heating and cooking at homes with hydrogen, that allows you to actually lower the footprint of this whole infrastructure with relatively low investment, because up to a certain content of the hydrogen in the pipelines, as have been mentioned in the presentations during this meeting, you don't need much change to the infrastructure. So it's either, I think it's going to be either this gradual transition and or the market disturbance technology, hopefully.
Very good point. Thank you very much. Very much agreed. Thanks, Roman. We have 2 more minutes, Gabriela. Should we start closing the meeting? And maybe afterwards you can send the contacts for
Yes, well, I would like to say I would like to remind one thing. The webinar is recorded, and we will send you the link if everybody agrees to go through it again if necessary. But I see in the chat one more question. Let's say it will be the last one. But may I read it? Do we have time for one more?
Let's do so, but I can also answer that question through an email, if that's okay.
Okay. Well, I will send it immediately after. Let's do it, because it's almost 11 o'clock, and I don't know how the presenters can stay or not. So let's say the last question from Mr. Třinecka-Železárny will be sent by email. As it was said, you have all the profiles with the contacts. At least those who send the profiles can be disseminated. You will get the link to the webinar, and from my part, it's everything. I just would like to express once more, really thank you very much for the very interesting and in-depth presentations. Sorry, and maybe I will ask Leila to finish to add, if necessary, to add something and finish the webinar.
I have nothing more to add. Thank you very much, everybody from the Czech Republic, from Norway, and from the Netherlands for the very interesting presentations. And we are looking forward to be connecting more strongly with the Czech Republic. And you have the contact details of us in Norway and in the Netherlands from all the companies that presented today. So please don't hesitate to contact us, and we are looking forward to establishing this relationship with Central Europe and specifically with the Czech Republic and the city of Ostrava. Thank you very much.
Thank you. Bye.
Thank you very much.
Thank you. Thank you very much, everybody. Bye-bye.
Thank you, and bye-bye.
Bye.